So why am I talking about type parameters and variance and things like that today? At Tendril, one of our products is home energy reports, and we collect information about how people use energy in their home, and we produce them these reports. When we built a new system to build these reports, we used a free monad pattern. I'm not going to describe what that is, but we had workflow stages that all extended a common base class. They were all parameterized with some report type. We had extensions to those report types for the different kinds of reports that we generated. And so there was inheritance and container relationships at many different places. And Scala compiler, it's pretty good, and occasionally you see things like this. Covariant type A occurs in contravariant position, what? And my colleagues came to me and said, Chris, I don't understand this error. Can you please explain it to me? And I tried to explain it to him, and I did a pretty lousy job. So I took another shot at it, did another explanation that was much better, and so I proposed this talk. So why should users and API designers learn about these kinds of topics? For users, you're looking at APIs, you're looking at documentation, you're trying to understand what you're reading and how to make sense of it. You want to know, what's this thing that I'm trying to call? What does it need to take? What's it going to return to me? How do I make it interact with my hierarchy? If I have any of these weird error messages, how do I deal with them? And the API designer, on the other hand, wants to decide what sorts of flexibility they want to allow when they write an API. What do they want to offer? How do they make some of those rough edges easier? And what do they do when they see these weird error messages? So Adrian Moores, he's well known for saying, I stopped worrying about variance by just adding plus minus until it compiles. He may have even said that this afternoon, I don't know. And his point with this is that the Scala compiler does a really good job of getting your back. Usually you can just trust this. But I think it's good for us to go a little deeper and understand what we're doing and what it means. And sometimes we just have to add plus or minus until it compiles and call the day good. So quick overview of what I'm going to talk about. First, we'll spend a lot of time on variance. Then we'll talk about constraints and how those constraints enable a pattern called type classes. And then at the end, I want to mention very briefly how these concepts appear in Dotty that's going to become Scala 3. So let's start kind of with the basics, inheritance and substitution. So all values in Scala have a type. There's an inheritance relationship between those types so that all types have a superclass, a parent relationship that goes all the way up to a top class called any. And they potentially have a subtype relationship if they have a child. They always have this child down to bottom, but they might define their other classes might be defined in there. We can then substitute these in places because references can store instances of one of the subclasses. And when we call functions, we can pass a subclass where we expect that superclass. And functions can return a subclass when they tell us that they're going to return a superclass. And this kind of pattern is really, really common. You've probably seen it all over the place. If you're doing cons on list, you're already seeing this pattern happen. You're having two different subtypes for nil or for cons. So there's this formal thing called Liskov substitution principle. It was Liskov and Wing, 1994. Something about let phi of x be a property, provable, blah, blah, blah. The kind of more user, human-readable version of this I pulled from Wikipedia. If S is a subtype of T, then objects of type T can be replaced with objects of type S without altering any of the desirable properties of that program. So I can use subclasses the same places that I use the superclasses and expect everything to behave the same way. Changing topic a tiny bit, let's talk about higher-kinded types. So a higher-kinded type, a type that contains or is based on another type in some sort of way. These might be generic. We usually call these parameterized types. They're contained or implemented in terms of some other type. So a specific example is list of int. That's a completely bound example. The more general, list of t. We substitute any other sort of t when we bind it to double, whatever, when we instantiate one of them. So this gives us kind of two different axes where this subclassing can happen. There's the container superclass and subclass relationship, right? We have sequences, and sequences are subclassed as lists. But then we also have this axis where the contents have superclasses and subclasses. Ints go up to any ref, and so on. If we look at the Scala documentation, I think the first part comes from the Tour of Scala. Variance is the correlation of subtyping relationships of complex types and the subtyping relationships of their component types. So the correlation of that one axis and the subtyping relationship on that other axis. And Twitter Scala School puts it a little bit more precisely, a central question that comes up when mixing OO and polymorphism. If T is a subclass of T, is container T prime a subclass of container T? So I've always felt that defining and thinking about variance in terms of superclass and subclass relationships, although it's technically accurate, I've always found that really confusing to think about and make sense of. What do we mean when we're talking about list of T is a super type of list of U? So instead, I suggest that we think about that Liskov substitution principle and apply that back into these. So we're talking about when can we substitute values? When can we substitute complex types, and when can we substitute the component types? If T prime's a subclass of T, can container T prime be substituted for a container T? And when those things can or can't happen is what variance is all about. So I think about this like substituting compatible machines, right? So Calvin's got his new and improved duplicator, and he's going to substitute that in where he used to use the duplicator before. And Hobbes, who's pushing the button that goes boink, is going to not really care or know whether it's the new and improved duplicator or the old duplicator. So a lot of the tutorials that you see use this domain example that's in terms of animals. It's not very interesting or compelling, but it's intuitive. So I'm sticking with that. Like as we go through these slides, I think it'll be easier to remember that a cat is a pet and a pet is an animal than for me to introduce some other sort of domain thing that you have to keep straight. So let's jump right into the three kinds of variance that we can see in Scala: invariance, covariance, and contravariance. So invariance says there's no subclass relationship. That means we can't substitute a container T and a container U unless T and U are the same type. Sorry, unless T and U are the same type. But subclass, so that's this one axis, right? But subcontainers can be substituted for containers of the same type, right? So I guess list sequence is not a good example. But if we made our own list sequence that was invariant, we could substitute that sub list for the sequence. And anything that's exposed as a var has to be invariant. We'll kind of talk about that a little bit more later when we see what problems come up and what that error message was that confused Jackie. So a few examples here. So I start with my invariant class, invariant wrapper. Parameterized in A. He's invariant. He has no plus minus annotation. He has a parameter A to his constructor, and he's going to expose a method that returns that A. So if I have a W and I define W as invariant wrapper of cat, then I can put an invariant wrapper with a cat into that. But if I try, actually let me do the sub first. So I have a sub wrapper that extends invariant wrapper I make my invariant wrapper of cat. I can substitute my invariant wrapper for my sub-wrapper for cat into my invariant wrapper for cat. No problem. That's this one axis. But I can't go the other axis. Invariant wrapper of animal can't take my invariant wrapper of cat. Now I can take an invariant wrapper of animal and put a cat into it because that's regular subclass, but anywhere I'm using that, I can't pull it out and know it's a cat. I pull it out and know it's an animal. And if I want to know it's a cat, I'm going to have to become untype safe and do some casting and maybe do some reflection and stuff like that, ugly stuff. So this very bottom one, when I try to do the wrong thing, I'm going to get an error message. It looks something like type mismatch. Found an invariant wrapper of cat, required an invariant wrapper of animal. In this case, the compiler's helpful for us. It gives us an example of why it came to this conclusion. Cat is a subtype of animal, but invariant wrapper is invariant in type A. Okay, so it helped tell us why invariant wrapper of cat was not an invariant wrapper of animal. But this is the first place that maybe catches you or your colleagues out, and they say, what does it mean that this is invariant? So covariance is the second type. Covariance is really good when we want to consume values from the thing. So in this case, we have a subclass relationship when the contents have a subclass relationship. So if U is a subclass of T, then I can substitute a container for U into my container for T. And that's useful when we want to extract the contents out of the container. So remember, I can use subtypes anywhere that I use the supertype, so instances of U can be used anywhere where T's are expected. That's good. A container of U is going to give me out U's, which are substitutable for T's, so they give me T's, so that's good. Therefore, the types are sound, so that works. But this is problematic when you add or change values, and we'll get to that in a couple moments. So an example of this. So contravariant wrapper, this time we mark it as covariant wrapper. We mark it as covariant with the plus A. The rest of the shape is the same. I take an A and I have a def that returns that A. And I want to pass this wrapper into some function doit. So I can call that doit function with covariant wrappers of cats. I can call that function with covariant wrappers of dogs. Dogs and cats are subtypes of animal. In this case, I did this example with cats and dogs and animals. If you remember back, I had animals abstract, so that's why I kind of ended up with this kind of example. But this also shows something that's why we might want to use covariance, right? We can write this doit function that knows how to do things about animals, and we can call it with different subtypes of animals that are wrapped, right? We might see this with many of the list functions, and we can use that same one because list is covariant, and we can pass different kinds of lists. But if we try to call that with a covariant wrapper of any is not a subclass of animal, so we're going to get an error, and that error is a little less helpful than the error we got before. It tells us there's a type mismatch, tells us what it expected and what it found, but it doesn't give us the hint about why those things weren't the same. Let's go the other way. Other way is contravariance. So contravariance is subclass relationships when the contents have a superclass relationship. Okay, so when the contents are superclasses, then we can use it. So if T is a superclass of U, then we can replace containers for T's where we need containers for U's. So this is useful for processors or consumers of values. And so let me walk through that same thing. So instances of U, T is a superclass of U, so U's can be used where T's are expected. Consumers of U is example backwards here. So if use our subtypes of t's, a consumer that takes a t can consume a u. So the types are sound if I pass a container of t's someplace that, a container of u's someplace that expects a container of t's. It's problematic when we return or produce values, and we'll get to that in just a second. So see how this gets confusing? It's not that bad, really, but especially when you think about how these relationships work to one another and when you can substitute in t's and u's in different places. So maybe let's look at that with an example. So here I've got an abstract class keeper, and the keeper can tend whatever this A is. So we've defined it as contravariant with the minus annotation, keeper of minus A. So we have a dog sitter, which is a keeper of dogs. And just to show kind of the shape of what this tend is going to be, because dog is now my A, tend is going to tend dog, return a unit still. We're going to have to define the same thing when we define zookeeper, which is a keeper of any animal, and a pet sitter that's a keeper of any pet. So I'd still have that tend defined. I just omitted it for brevity on the slide. So now I'm going to want to think about when I can substitute in different kinds of pet sitters or zookeepers to keep my different animals. So if I have a keeper of dogs, I can use a dog sitter for that. Dog sitter is a keeper of dogs, and that dog sitter can tend Tintin, no problem. A zookeeper, because a zookeeper is a keeper of any sort of animal, it can tend any sort of animal. He can also tend Scooby the dog, because the dog is the animal. So we can substitute him in there, and that's fine. So I've still got keeper of dog, but I'm putting it in with a keeper of animal, which is a super type of dog. I can do the same. Can I do the same? I cannot, yes, I can still do the same for, I see what I did here. So if I want a keeper of pet, and I try to replace it with a keeper of dog, with a dog sitter. Dog sitter is a keeper of dogs only, but it is not a keeper of all sorts of pets. It's just a keeper of dogs. So my dog sitter can't sit cats, can't sit hamsters. So I'm going to have a problem if I try to send my dog sitter, send my cat to a dog sitter. So my error message, I found a dog sitter, but I needed a keeper of pets. Dog is a pet, but dog is not the keeper of all, or dog is not all kinds of pets. So now we have enough to come back to the error message that was making Jackie throw up his hands. So that error message talked about covariant value in contravariant position. So what are positions? So the spec defines a bunch of rules for what makes a position and how positions change. But in practice, usually what you carry about is covariant position is method returns. Contravariant position is method arguments. And invariant positions are mutable vars. So when we define in our type parameters, plus A, minus A, or nothing, we said whether that was a covariant, contravariant, or not invariant type parameter. And then we're going to look at the positions. Covariant parameters, ones that are marked plus A, cannot appear in contravariant position. That means in a method argument. Contravariant parameters, minus A's, cannot appear in covariant positions, method returns. And neither covariant or contravariant parameters can appear in an invariant position. So the error messages that come out of both 2.12.6 and IntelliJ, unfortunately, are a little bit misleading because they still give you the same error message that says covariant parameter can apply in contravariant position instead of saying covariant parameter cannot apply in invariant position or something like that. So what's the problem with these? Why can't we have something appear in the wrong position? So let's look at contravariant first. So contravariant is method parameters. So if I try to do box of a pet plus pet, so covariant pet, and I try to do a swap that puts a new pet into the box, I'm going to get this error message on that swap method, which is new p. So suppose I have a box of cats, and I want to swap the cat. Okay, that would be a fair thing, right? I've got a box of cats, and I want to replace it with a cat, no problem. If I have a box of pets, and I want to put a cat still into that, that seems kind of okay. But if I have a box of cats, and I try to put a dog in, now I've got problems, right? So I have my box of pets. I instantiate that as a box of cats, and then I try to put a pet in, and that pet's not a cat. Ruh-roh. So that's the problem with contravariance, and that's why covariant parameters cannot appear in contravariant position in value A of whatever. Opposite is the case for covariant, right? So covariant position is return types. So I have a sitter of contravariant pets. I'm going to instantiate my sitter with a setter of any pets, and I try to walk that pet. That seems fine. In this case, I have this walk method, and walk's going to return a new pet. So I've got my sitter of cat, and my pet sitter returns me a new pet. If that pet's still a cat, okay, everything's fine. If that cat returns a dog, we have a problem. But that's perfectly legit for the sitter of pet to return any subtype of pet, right? So that's why this is a problem to have contravariant arguments appear in covariant position in value whatever of whatever. Let's look at a different sort of example, and we'll look at a couple of things from this. So one is I want to make a point about multiple parameters and mixing and matching covariance and contravariance. So I have some P1 that's a pet and some P2 that's a pet, and I'm going to call a function f with those two parameters. So I have a bunch of example f's here, example definitions for f, bunch of different signatures for f. If I just had f of pet, which of these signatures would I be able to call? So f that takes two pets and returns a pet, yeah, absolutely, I could call that with P1, P2. F that takes an animal and a pet and returns a pet, and I call it with two pets. Yeah, cool. F of any and pet, and I call it with two pets. Pets are still any's, yeah, good. F of any pet. Pets are still any's, yeah, good. F of cat and dog. Cats and dogs are pets, but pets are not cats or dogs, right? I can substitute the one direction, but not the other direction. So with just f of P1 and P2, I couldn't call this last f. So what does that all say? That says when make sure I say this carefully. If I wanted to substitute a different function, I could substitute any function where the inputs are supertypes of the way I'm trying to call it. Okay, so I have f of two pets. I can substitute in any function where the parameters are pets or above. Pets, animals, any. And that's true for any of our arguments. So in this case, function 2 takes two parameters and returns a result. So we see function 2 has 2 inputs and 1 output, T1, T2, R. This generalizes across all 22 different function types, so function 1 all the way to function 22. All these inputs, because they can now I can substitute them in when they are super types. What does that mean? That means contravariant. And I deliberately have left my R blank here because we'll get to that on the next slide. So now I'm defining a type that I expect to come back from those functions. So R, that's an animal, and I'm going to call F with my 2 pets. So if I have an F that takes 2 pets and returns an animal, yeah, I can store that into an animal. Okay, cool. F that takes 2 pets and returns a pet. Pet's an animal, so I can store that into an animal. Okay, cool. F that takes 2 pets and returns a cat. Cat's a pet, pet's an animal, so yeah, cat's an animal. F that takes 2 pets and returns an any, well, no, any's not an animal. Any may be, animal is, so maybe, but in general it's not. So what does this mean? This means we can substitute in these functions when they return subtypes, so covariant. So our function 2, and again, by generalization, all of our function ends, are contravariant in inputs and covariant in responses, in returns. So again, when to use these. So covariance is really good for containers when I want to get things out of that wrapper, out of that container, out of that list, out of that whatever. I want to be able to substitute in other wrappers that have subtypes of those. So anything that's a kind of a producer, anything that represents inputs, that should be the opposite, represents outputs of the thing that I am calling. And contravariance, I'm going to use when it's something to consume, right? So our examples were zookeepers and pet sitters that consumed in some way a pet, but these could be processors, printers, what have you. Something that's going to visit everything and wants to be able to do those. And the idea there, right, is that because that processor can process some supertype, it can process some part of the thing I'm passing, and I can pass it some more refined thing, and it can still process the parts that it knows. And again, this is flipped on the slide. It'll be fixed by the time I upload these, representing inputs to the thing. So back a number of years ago when Java introduced wildcard parameters, Josh Block came up with this mnemonic. This mnemonic works a little better in Java because of the keywords, but I think it's still useful and still helps us remember that. So think Arnold Schwarzenegger and his fantastic pecs when he was a young man bodybuilding, Mr. Olympia. And producer extends, consumer super. So when it's an extension, when it's a subtype, we use those for producers, covariance. And when they're consumers, that's when we want to do the supertypes, contravariance. Okay, so constraints and type classes. So we'll start with some simple ones. Upper bound and lower bound are for same or subtypes. So this is when we want to say, so my examples here are functions. So this pet function, this is pet like apply love to, apply love to a pet. This pet is going to take any p which is a pet and do something. So I'm not going to allow myself to pet other animals that are not subtypes of pets. I guess depending on whether or not you define insects as pets, or not. Lower bounds go the opposite way. The parameter is the same type or a super type. So this pre, I think, was meant to be add a prefix to a list or something like that. So I want to add B's to a list of A's and return a list of B's where B's are supertypes of A's. And I have an example of this on a couple of slides that'll explain a little better why this B and A and what's going on with this one. But this is saying we can call P pre with any X, which is a B, which is a supertype of A. So bounds and variance. So this is kind of the same problem that we looked at before. This is a plus A covariant parameter, and I'm passing it in as a method argument, contravariant position. So this is going to be the same error that made Jackie throw up his hands at the beginning, right? And I explained before why that was a problem, but we didn't talk about how to solve it. So one of the things that we might try is we say, okay, well, let me change my types and let me just use B's and let me prepend B's onto this list of plus A's. But then there's no relationship at all between A's and B's. So the compiler doesn't know what to do with these things. You know, I had a list of B's or a list of A's, and you've given me a list of A's, and what do I do? So we need some sort of relationship between B and A that's going to be sound. So we're passing in any B, which is a subtype of A, and a new B, and we're going to yield a new list of B's, right? So I have a list of, say, ints, and I want to pass in some new any. Any is a supertype of int, and I'm going to return a list of any. Right? So what this is doing is it's changing the type to a wider type. And this is exactly what happens with list. Actually, this is exactly the shape of what the real definition of list is here. Covariant, prepend can take any B, which is an A or a supertype. So we're going to start with a list 1, 2, 3, 4, 5. We cons a 0 onto the beginning. We still have a list of ints. 0 is an int, is supertype bound, is satisfied, int or supertype. If we try to instead cons 1.5 on, well, 1.5 is a double. So we're going to have to widen to something which is the lowest upper bound of double and int. So we're going to end up with any val. So now we've turned from a list of ints to a list of any vals. Was this safe? Yeah, absolutely it was safe. 1.5 is a double, double is an any val. All those things I had before were ints, ints are any vals. So now I have a list of any vals. But when I want to get things out of it, I get out any vals. And if I want to figure out what they are, again, I'm going to have to go type unsafe and do some introspection or do some typecasts or stuff like that. View bounds, I don't want to say very much about this. These were deprecated. I just have a slide in here in case you still see them in the spec or in real code. They're still in the spec, even though they're deprecated. Basically just indicates that A is convertible to B by some implicit conversion, which introduces an evidence parameter that we can use to do that conversion. So more interesting, though, is context bounds. So A : context means that A has some context, which means that context of A is somewhere in the implicit scope. And this is going to introduce, the compiler is going to introduce an evidence parameter. And this evidence parameter is passed as an implicit parameter. Looks like, so I have context bound of X, which is an M. And so I get my regular, whatever my regular argument list is, and then I get added to my implicit arguments this EV$1, which is an M of X. And then inside my method, I can use the implicitly keyword to summon that M of X and start calling methods on it. So that lets us use something called type class pattern. So type classes let us implement interfaces externally to the code. So I have some existing class hierarchy, and I have some new interface that I want to implement, and I don't have access to the original code, or maybe I don't want to touch the original code. I can write an extension that we call a type class outside of the original code. I can use a context bound to say this gets passed to, this can be passed anything which has a context of that interface. What's cool about these is that we can then implement them in terms of other instances. So if I have an adder type class and I have an adder of int, I can implement adder of pair of ints in terms of that. And the compiler can wire that up for me. And that generalizes really, really powerfully because I don't have to know what the t is. As long as the compiler can give me an adder of t, I can now implement adder of pair of t. And that generalizes even further. Shapeless and so on do a lot of fancy tricks with this to generate type class derivations for you automatically. Miles used a fancy word earlier today, inductive type class derivation. So simply put, that's define an interface, implement it for your class, put it in implicit scope, pass it to the function as a type constraint, call methods from the interface. Sounds easy enough. So there's my adder of A's. It's going to have an add method that takes two A's and returns an A. So in implicit scope, I'm going to define an int adder that's an adder for ints that takes int and returns an int by delegating to the regular plus. Then I can add things. I have some list, say, that wants to go through and add things. I want to go through a list and add things. I call this add things method with any t that has an adder context. And my add things can then summon the implicit type class instance for whatever that t is, call add on it. And Robert's my mother's brother. Quickly, I want to mention how these concepts come up in Dottie and Scala 3. Good news, Martin told us yesterday, Scala 3 is fundamentally the same language as Scala 2, and that is true for these concepts that I talked about today. So variance and type bounds all still exist in essentially the same way. The current compiler, the error messages that it returns are slightly different. And right now, slightly less helpful. I still got the same position error that made Jackie throw up his hands, but I got a different error for one of the other cases. I didn't talk about existential types. Those are going away. And structural types, which I also didn't talk about, essentially duck typing. Still exist, but they're implemented differently. So it'll be interesting to see whether those get used more as their new implementation is more efficient. So that's all I have. You can find me on Twitter. Eventually, all these examples will all be up on GitHub. They probably will not be as up to date as the slides until after the New York version of this conference, but you can look, some of them are already there now, and these slides will be made available as well. So that's it. My timer just said 45, but he told me I have 5 more minutes. So if I have a couple more minutes, I can take a couple questions.
On one of your slides, you mentioned that vars require invariance. please correct me if I'm wrong, but I think var cannot do that. So you can assign a covariant list to a var. It's related, I think you meant the mutable collections instead of var.
So, okay. So the question is, actually you're on the mic, so do I need to repeat? I'm not sure. So if the var is exposed, so you can see it outside the context of your class, then it has to be invariant. If you use it internally, if it's private to the class, then yes, you're right, you don't have to.
What happens then if I assign a list to a var? Immutable list, which is covariant. Yes.
If you assign a list to a var.
Yeah, covariant list. Yeah, it's just, you meant mutable collections. It's really, it's just a typo.
Yes. So, right, I'm just trying to figure out how best to kind of answer this. So I believe if we are going to expose as a public member that list, that we are going to get a compiler error, and I think it's going to be a compiler error that looks very much like the position error that we saw before. If we have that as a private member and we store a thing into it, then we should be fine. Let me see if I can pop out and take a quick look in. Okay, so I don't have an IDE up, so I'm not going to pull this up now. But the problem that happens when we try to expose the mutable variable is very similar to these problems that we see with positions. We're going to have the ability to try to store things into that variable which don't match the variance of the variable. Right? So the same problem that we have here where contravariant positions we are going to be able to construct a case very similar to this one. Let me pull this back up. We're going to be able to construct an example very similar to this where we try to set a new value. So if we had a box of cats and we tried to change that cat to some other type, we could end up trying to store an animal into that cat which is not a cat. Okay, so thanks for your question. We can talk about this a little more afterwards. Thanks everyone for listening.